A function f of x is continuous at x equals a if the limit as x tends towards a of f of x equals f of a. Let's suppose our function f of x looks like this. Now, again, we're dealing with single valued functions. That's the only type of function that we deal with. So, for example, when x equals minus 2, the value of the function is 2. We don't have another value of the function. This point has been removed. So if we draw a vertical line through minus 2, it will cut the graph at just one point, namely the point minus 2, 2. This point has been removed. Similarly, at x equals 3, if we draw a vertical line, it will cut the graph at just one value, namely the point 3 minus 1. The point 3, 0 has been removed. Note that f of minus 2 is equal to plus 2, but that the limit as x tends towards minus 2 of f of x does not exist. So that means that if we approach minus 2 from one side, well, we can see the limit is plus 2 if we approach minus 2 from the left, but if we approach minus 2 from the right, we see our function approaches minus 1. So we get two different answers depending on which side we approach minus 2 from. If we get different answers, then we say that this limit does not exist. Now, for the function to be continuous at the point minus 2, then the limit as x tends towards minus 2 of f of x ought to equal f of minus 2. That's the definition of continuity. We just plug a in for x. In this case, we plug minus 2 in for x. But since the limit doesn't even exist, we can't say it's equal to minus f of minus 2. So it's not equal to f of minus 2. So that means that the function is not continuous at x equals minus 2. As a matter of fact, we say that there is a jump discontinuity at x equals minus 2. Notice that f of 0 is equal to 1. Notice also that the limit as x approaches 0 from either side, either from the left or from the right, is 1. If x approaches 0 from the left, we can see the graph is approaching 1. If x approaches 0 from the right, we can see that the graph is also approaching 1. So this limit exists and is equal to 1, but 1 is just f of 0. So to get this limit, we just replace x with 0. That tells us that the function f of x is continuous at x equals 0. Intuitively, that makes sense. There are no breaks in the curve. There's no break in the curve at x equals 0. By the way, the curve is smooth at x equals 0. It doesn't have to be for continuity. The curve could have looked like this. We could have a sharp corner. You know, the curve could consist of two straight lines whose corner is at the point 0, 1. We would still say that the function is continuous at x equals 0. As long as there is no break, it doesn't matter about that point, whether it's on a sharp corner or on a smooth section of the curve. Finally, note that f of 3 is equal to minus 1. This point has been removed from the curve. So this is a point of the graph. 3 comma minus 1. F of 3 equals minus 1. But if we take the limit as x tends towards 3 of f of x, we get 0. So if we approach 3 from the left, we can see that the function is approaching 0. If we approach 3 from the right, we can see that the function is also approaching 0. You know, if we go up to the function, take any point just to the right of 3, go up to the curve in a cross, we get a number that's just above 0, and we get closer and closer to 0 as we pick our points closer and closer to 3. So this limit does exist and it's equal to 0, but it's not equal to f of 3. We can't calculate this limit by plugging 3 in for x, because f of 3 is not equal to 0, it's equal to minus 1. So the function is discontinuous at x equals 3. As a matter of fact, we say that there is a removable discontinuity at x equals 3. So it's like we removed this point from the curve and shifted it down so much, or we could have shifted it vertically up some distance. In this example, we are going to decide where the function h of t equals 4t plus 10 over t squared minus 2t minus 15 is not continuous. To do that, we are going to look at values of t that make the denominator 0, because when the denominator is 0, then the function isn't even defined. Okay, if we factorize the denominator, we get t minus 5 times t plus 3. If the denominator is 0, it means that t equals 5 or t equals 3. So the function is not defined at t equals 5, and it's not defined at t equals 3. So that means if we take the limit as t tends towards 5 of our function h of t, we will certainly not get h of 5. Okay, that's the condition for continuity. We need this limit to equal h of 5. But h of 5, the function is not even defined at t equals 5, so h of 5 doesn't even exist. Similarly, the limit as t tends towards 3 of h of t is not equal to h of 3, since the function is not even defined at 3, because we get division by 0 if we let t equal 3. Actually, this should be t equals minus 3. Okay, so the limit as t tends towards minus 3 of h of t is not equal to h of minus 3. So here's a picture of the function on GeoGebra. Here's t equals 5. So if we approach 5 from either the left or the right, well, we are not approaching a unique value. The limit doesn't exist at t equals 5. If we approach 5 from the left, then the function is heading towards minus infinity. If we approach 5 from the right, the function is heading towards plus infinity. Similarly for t equals minus 3. So the limit doesn't even exist at these points. So we can't talk about the function being continuous at these 2 points. At the very least, the limit has to exist at the 2 points for the function to be continuous. And not only that, the limit must equal the value of the function at the 2 points.